So welcome back students. Today we will start a new chapter, chapter number 4 from your textbook. Okay. So this is about transient vibration. So transient vibration. Okay. Okay. So transient means something that varies with time. Okay. In contrast to the steady state. So this in chapter 3 we studied the steady state solution. So given the periodic load, then the displacement is also periodic, yeah, and that's the steady state solution. So given the input as periodic input, the output is also periodic. Okay. However, we want to know if how the displacement varies as a function of force, or force could be of any kind. When we say kind, means force could be something like, for example, we have at some time t, say let's say t equal to tau, and there is just some impulse of force there. Okay, so or you can also write as delta t minus tau, right? So delta is also here is a direct delta function, right? So that really means you can also write like this: delta t minus tau equal to 1 if t equal to tau, and equal to 0 otherwise. Okay. So there could be certain impulse, small force, yeah, and after that we want to find out how a spring damper system. So still we are on a spring damper system, and we are trying to find out now that given a force Ft of any kind, now if sinusoidal we have seen, now we want to focus on any kind of force and how the solution, how the x will look like. So one force could be something like this one, or we can say F equal to F naught delta t minus tau. That means at t equal to tau, there is a impulse of force given, that's it. And after that we want to find out how the displacement is, how the displacement looks like for this. This is case 1. Okay. Now case 2 could be, number 2 could be, let us say, one unit step function or a step function, a step input. So from here to here, this is ut. Okay. When you say ut, you can also write if it starts from here like this one, tau, you can also write as ut minus tau, right? That means equal to 1 for t greater than equal to tau, and equal to 0 for t less than tau. Right? So here your force, our force could be a unit step function, could be a step function, meaning that it could be something like F naught u t minus tau. Right? This could be like this, means at time t equal to tau, you have pulled it with you have just applied a force, and that force will be applicable, like something like a electromagnet you have. Let us say a spring mass damper system. So this is K, see like this, and let us say this is M. This is made of iron, for example, and you have electromagnet here, and what you do is switch on the magnet, and then it applies a force on that. Okay. And let us assume that there is a constant force which is applied there. And that force continues as long as you have switched on the electromagnet. And under that condition, how the vibration will be, that you have to find out. Yeah. So I'm just giving an example. We will also try to solve them. Okay. How will not try to? We will solve them. Okay. So the condition 1, case number 2, case number 3. So this is call it impulse input. This you call it a step input. And let us say there is a ramp input, right? So ramp input. So these are just examples. There could be many, but if you are able to solve this, then you are able to solve any kind of input as long as you have a linear system, something like this. Yeah. So okay, now this is a ramp input. When you have ramp input, then it goes something like this. Let us say like this. Yeah. So you have T here, and here you have F. So F is given by, let us say, equal alpha times T. Yeah. So at T equal to 0, F is 0, and it is increasing. Yeah, it is a straight line like this. So that really means that if your force is increasing with time here, you have from 0 to it is keep on increasing linearly, then what kind of displacement this mass will have, that we have to find out. So these are all the examples, and in this chapter we are going to study that. In fact, we will, after solving this, we are going to extend that to any general purpose force. Our force could be something like this. It's a varying with time. So we should be able to calculate the response xt for any type, any given force. Okay, so that's the objective of this chapter, and we are going to learn it. Now let's start with the impulse input. Okay. Now, what is the meaning of that? Meaning of that is, this is the force looks like something like this. Okay, like this one. Yeah. Even this is how this is a unit impulse. Okay, unit impulse. Either you write it as delta t minus tau is equal to 1 for t equal to tau equal to 0, otherwise, right? So otherwise, you can write like that, yeah? So let us say this kind of, the force is given, as I said in the example, if the force is F equal to F naught delta tau minus tau. Like if you have a force like this one, then how to find out? Okay. Now we will simplify meaning that you know that if from here to here it is tau, so you know that when t is less than tau, no vibration. No vibration, there may be some vibration to begin with, okay, but in this, here we are assuming that our spring mass damper system, the case like this one, is at rest. Okay, it is at rest, meaning that x0 equal to 0, x dot equal to 0. We are assuming this to begin with. Okay, so that really means for t less than tau, there is no vibration. Yeah, there is no force applied, it is just hanging out there. And then suddenly at t equal to tau, there is a impulse applied, force applied and released. Applied and released. Okay. The force is F, we can write it as F equal to F naught delta t minus tau. However, the real meaning we will also understand today. Okay, so what is the meaning of that is for t less than tau, there is no vibration, and there is a vibration for t greater than tau. There is vibration. There is a vibration, or what I mean to say is ut is not equal to 0. Right? So there will be some expression for ut if t is greater than tau. So this problem, this one, you can also rewrite it as f equal to f naught delta t, meaning that if we know the solution to this one, we can also find out the solution to this one. This really means is your force is being applied at tau equal to 0 itself, or t equal to 0 itself. At t equal to 0 itself, there is one impulse being applied. The force being applied suddenly and released. Yeah. Okay. So we are going to find out for this one, and accordingly we can write solution for this if you know the solution for this. So this problem being converted into this problem. Here the impulse was being applied at t equal to tau. Here I am going to apply t equal to 0 itself. Okay. So whatever is the solution here, let us say our displacement, what we get is like this one. We get the solution, in this case the same, but our solution starts from here. Here it are from t equal to 0. Here the same thing, same u, if you place it here at t equal to 0, so t equal to 0 becomes t equal to tau. This is a new solution here. So basically, once you know this one, you can find out this one, right, in this case. Okay. So in any case, okay, so our problem now simplifies to basically f equal to f naught delta t, and if you want to find out, if you know the solution of this one, we will find out the solution of this one. And what is the problem? From here, if you recall, mx double dot plus cx dot plus kx equal to f. Right? So now there is a general force f applied, so ft. Right? So equal to ft. But in this case, what is f? F equal to f naught delta t. Yeah. So we straight away we can apply the Laplace transform, right? So apply Laplace transform and see what happens. We get m s square minus x, the x at 0 s minus x dot at 0, okay, plus c, then here also we have to write m, then s square xs, yeah, okay. C s xs minus x0, okay, plus k xs, and then we have to find out the Laplace transform of this f naught times direct delta function. And for this one, the solution is, for this one is 1, simply 1. So this becomes f0 is a constant, and Laplace transform of delta t is 1 actually. So multiplied by 1 equal to f naught. And okay, so what we get finally, okay, so finally our value becomes here m s square plus c s plus k multiplies by xs becomes equal to, and we have f naught here, so f naught plus, okay, f plus, and we have m x at 0 s okay, so we get this one plus m x dot 0 plus c x at 0, so we get this. Okay, and finally x s, okay, so that becomes equal to f naught plus m x s plus m x dot plus c x at 0 divided by m s square plus c s plus k. So xt will be simply equal to the inverse Laplace of this function, right? f0 mx s plus m x dot 0 plus cx at 0 divided by ms square plus cs plus k. So general, we found out this way. As we know, it all depends on zeta, where zeta is c over 2 root kn, and accordingly the solution will be different. Yeah. So let us say we want to apply this one to a simple spring and mass system only, right? So for this, if f equal to f naught delta t is the force, impulse force you apply, then what kind of x t will be what in this case? So we make c equal to 0 in this case, and let us see what it looks like. Okay. So here you have assume the c equals to 0, okay, for undamped vibration, and what we get? We get xt is equal to L inverse, and we have f naught plus m times x at 0 s plus m x dot x at 0 divided by ms square plus k. So this is what we get. Yeah. Okay. Is equal to, there is m is common on both sides, so we can just write f naught over m plus x naught s plus x dot 0 and then s square plus k over m, which we know that omega n square. So this we know already. So that becomes equal to what? We have, that really means we have L inverse f0 over m plus x dot 0, okay, and divided by s square plus omega n square, right, plus we have x at 0 s over s square plus omega n square, right? So what do we get? We get here this term. You know that if you take inverse Laplace transform of this one, you will get f naught over m plus x dot 0 and multiplied by 1 over omega n, and then this becomes sine omega n t. And this term, this is because Laplace transform of sine omega n t is omega n divided by s square plus omega n square. That's why you get like this. Yeah, and this terms becomes x at 0, and this is cos omega n t. So this is the solution. If at t equal to, if we assume it was at rest to begin with, yeah. So it was if x 0 equal to 0 and x dot 0 equal to 0, yeah. So initially they were rest before there was one unit impulse which was applied, not unit impulse, but F, the impulse force F equal to F naught delta T was applied. If this, then what you get? You get equal to, this term is 0, this term is 0, what you get is F naught over M, then omega n here, and sine omega n t. So, which term you get? xt. So, we get xt is equal to this one. So, given F naught, so this is solution of what? When F equal to F naught delta T, then solution is this. So a spring, if you apply a spring mass system, if you apply force equal to F naught delta T, means it's impulse force. You just apply a force which lasts for very small time. Okay, and then what do you get? You get solution xt, which looks like this. That means there will be a sinusoidal vibration. Okay? Mass hanging from a spring, if you give a force F naught, which is applied to very small time, and then it will automatically start a vibration, okay, whose amplitude will be F naught divided by M omega n, right, sine omega n t. Okay, this is what we get, right? So this is the response because of a impulse force. Response because of the impulse force. Now we will see whether this solution that we obtained makes sense. Yeah. So what was the problem? Problem is the spring mass system. You applied force F equal to F naught delta T, and you find out xt, and you found out that xt is equal to F naught divided by M omega n sine omega n t, right? And so I will not write it here. We will find out different way. Okay, same solution. If we can find out, apply physics as well. Yeah, here we applied a mathematics basically, or in other words, let's see what is the physical interpretation of this. Yeah, so we are applying a impulse force. Impulse force is basically, you can also say that a force is something like this. So this may be distributed, this is t, right? So let us say this time is very small time. So delta tau, let us say, or delta tau, okay? So when you say unit impulse, that really means from here to here, this will be 1 over delta tau. So that total area is 1. Okay, so that total area is 1. So to unit impulse, total area is equal to 1 unit. Yeah. Okay. Now, if you have applied F naught, let us say a force F naught for some time. So basically, you can write F our force was F equal to F naught delta T. Okay. Here, delta T, the meaning of delta T here is basically if a function which looks like this one, whose width is delta T and height is 1 over delta T. Okay, so this is something like this. Okay. Let us say we have a impulse. Impulse is defined as, you say F, right? F T dt, right? You say impulse, right? Okay. We can say F hat as Ft 0t, where this will be applied for very small time. So 0 to delta tau, you can say. Yeah, you say being applied for very small time, right? For example, this one. So that really means, what do you mean by here? This F naught is equal to delta tau. Ft is nothing but this. So F naught delta t dt, and that really means, what do you get? The value will be F naught, and this will be as delta 0, if this value is 1, right? And all others it is not, basically, right? So what do you get? We get F naught, and that's it. The value, what do you get, is like this. Yeah. So basically, what is the meaning of that is, basically, when you say the impulse force which is Ft multiplied by time, which is a force multiplied by a small time, right? And then you are integrating the whole thing. And after integration, what we find is F hat is F naught only. So this one, F naught is nothing but, this is the impulse, force impulse. That means a force Ft being applied for a small time, right, from 0 to delta tau, and that is what you replace it here. So F naught here is nothing but the force impulse, the force integrated over time, right? So this is what the meaning of F naught is in this case. Yeah. So that means for impulsive force is represented like this one. You have delta t here, delta tau here, and here this is F. So this one is nothing but F naught over delta tau, like this one. So that if you integrate, you get F naught. So F naught is the impulse, force impulse, right? So F naught is nothing in this case but equal to F dt, right? In fact, in this case, even you can integrate from 0 to infinity and you get F naught only. So this is how the representation of a impulsive force is. This impulse of a force, which is the integration of force multiplied by dt. Of course, in this case, this is acting for a very small time, right? Because the direct delta function representation that shows that this is acting for very small time, right? Very small time duration. So anyway, so the idea is when you say F equal to F naught delta t, that there F naught represents the force impulse, that is one force of magnitude F naught over delta t applied for over delta tau being applied for delta time, delta tau time. So like this. Okay, if that is the case, if f naught is the f naught is what? F naught is equal to f dt. You can write like this one. F naught equal to f dt, right? And that we know that we have the if we know f equal to, we have m dv over dt. So f equal to, if you apply a force, there is going to be one acceleration dv over dt, right? And that means the f times dt will be m dv, right? Okay. But f dt is nothing but f naught. So f naught will be m dv. Now this our system is at rest initially at t equal to 0, right? And you are applied a force. You have applied a force there for a very small time, and it will increase the velocity by how much? By this much. So velocity, actually, this is at rest. Then you have applied one impulsive force, and then what happens? Within very small time, displacement will not change, but the velocity will change. Okay? So a spring mass system, you suddenly applied impulsive force. So what it will do? It will change the velocity, right? And that initial velocity will be equal to initial velocity. That will change the velocity. Initial velocity will be dv equal to f naught over m. Will be the velocity. Yeah. So that means x dot 0 equal to f naught over m. This is the initial velocity that it imparts. Okay. Now we have to remember the free vibration case when a spring mass system. So I'm going to do this one. If there is a spring mass system under free vibration, Km, free vibration, okay, and if you solve it, what do you get? You get actually xt is equal to x dot 0 over omega n. Yeah, and then you have here sine omega nt plus x 0 sine omega cos omega nt. Cos omega nt. Now, so a spring mass system is there. Force, suddenly you applied a force, and this is going, this what it changed. It that instant only, at t equal to 0 only, it changes velocity, to which from 0 to f naught over m. This is the velocity it has changed. So that means if the initial velocity x naught 0 equal to f naught over m, initial displacement equal to 0, then what is the vibration? Displacement is given by, you put it there, okay, f naught over m omega n, and then sine omega nt. And x 0 is 0, so hence you get the same displacement here what we got here actually. This we got from mathematics. We applied the Laplace transform, inverse Laplace transform to get this one. Here what we did, we applied the physics. we saw the one, what is the meaning of force impulse. Then a force is being applied for very, very small time to a mass, and from there we saw how it changes the initial velocity. Okay, it changes the velocity at and that initial velocity we have applied here in from the, this is a free vibration solution, from the free vibration solution, and what we get is a displacement in this form. So what we see is both are the same actually. Yeah. Also you should notice the units. What should be the units? If you see xt, it says f naught over m omega n sine omega n t. If xt is in meters, then see the what should be the value. So f naught, we want to find out what is the units of f naught. Yeah. So you want to find out f naught. We have, this is meter multiplied by, this is m is kg mass, and then omega n is 1 over second, radian per second. So meter, and then kg meter per second. Kg meter per second, right? So m times b times, right? That's what we expected. Equal to, you can also write kg meter per second square multiplied by s. So Newton per second. So this is indeed a impulse, right? Unit of an impulse. Like that. Yeah. So basically now, since f naught is a unit of impulse, that is Newton multiplied by s, so unit of f naught over delta t, where delta t unit is second. So this unit will be in Newton. So basically what it shows is a load, some Newton force is being applied for some times delta t. That's what it says, right? Such that the integration is f naught, so f naught is an impulse. So remember, whenever we are saying a unit impulse, that tells you what is the physical meaning of that. When you say f equal to f naught delta t, if this is a force, this is represented by this one, where f naught delta t itself, that really means is equal to 1 over delta tau, as we have seen earlier. So keep that in your mind. Okay. So next, if you want to find out the for unit step function, okay. So what we mean to say is, suddenly at t equal to 0, you have f naught here, f naught, right? So f is given, this is t, this is f. So f is given by f naught unit step function ut. Yeah. So that means at t equal to 0, no force, and suddenly you have applied the force. So this looks like there is a spring. Again, let's study a spring mass system only. So it is the same. You can extend that to a spring mass damper system, right? So if this is the mass, okay, we can also include this one. Okay. Now this k c, and then you apply the force F equal to F naught ut, where ut means ut is unit step function. Okay. Okay, so first you write your equation mx double dot plus cx dot plus kx is equal to ft, which is equal to f naught ut. Take Laplace transform on both the sides, x dot plus kx equal to Laplace transform f naught ut. Or you say m, then s square xs minus s x0 minus x dot 0 plus c s x s minus x0, yeah, then plus k x s equal to f naught, and Laplace transform of ut is nothing but 1 over s. Okay, is equal to f naught over s. Yeah. So Laplace transform of a unit step function you can get from standard book. Also you can consult Wikipedia, for example. You get from list from there also. Okay, so this so finally what do we get? We get xs is equal to let me write directly, so now since same thing is going to appear again and again, so what do we get? We get msx0 plus mx dot x0 plus cx0, okay, divided by m s square plus cs plus k plus we have this term as well, yeah, so plus f naught over s ms square plus cs plus k, we have this also, yeah. So we have to find out xt. Of course we have to find out, we can have together, so if we multiply, we can multiply s on both the sides, so finally what we'll get, we get or maybe we first write xs equal to and then we get m here, but divide by m already here, so that way we will have okay, just multiply only. So we get ms square x naught plus m s x dot 0 plus cs x0, okay, plus f naught, okay, and divided by we have m s q plus cs square plus k ks. Okay, and we can find out xt, which will be the inverse transform of xs, and we can find out from there. So again we can sort it out, we can find out, okay, for if we want it for let us say bit c equal to 0, okay, so undamped condition, undamped, okay, so then what do we get? We get in that case xs will be equal to with, okay, so undamped, and also we are putting x dot 0 equal to 0, x0 equal to 0 as well. So with, to simplify, we want to just see for a spring mass system only. For a spring mass system only, we want to find out what is the xt in that case, yeah. So xs will be equal to this is 0, this is 0, this is 0, yeah. So what we get? F naught simply xs equal to, we get f naught divided by m s q plus cs square plus ks. Yeah, okay. Okay, one mistake here. So c is 0, so what we have is plus ks only. Okay, so f naught over m, and what we get here is k over m here, so s cube plus omega n square s, which will be equal to 1 over f naught over m over s multiplied by s square plus omega n square. Yeah. So we need to simplify this one. So we can write it as f naught over m, and here, so we have to make something like a over s plus b over s square plus omega n square. Again, we will have probably in this case this s only at least, so that we square it here, and then we have this one, so c will be 0 in this case. So this will be of this form, something like this one. We can actually exactly figure it out how much it is. So okay, so this one, so just to remove this also, because this is for simple spring mass system. So what do we get here? So xs will be equal to f naught over m, and we can see that if we have 1 here, so this will be 1 over s, and here it will be minus, probably minus, so s square plus omega n will be here, minus we have 1 here also, s square plus omega n square, and then we have 1 over omega n square. So we have omega n square here divided by omega n square. So we get this, yeah. So is equal to, we get f naught over m omega n square, and here we have 1 over s, and then we have minus, then we have here we can write omega n over omega n here, and okay, and here it will be s square plus omega n square. Yeah. So xt inverse Laplace of xs will be equal to f naught over m omega n square, and then we have this. So what is the meaning of this? This one is of 1 over s is nothing but unit step function only. So we have unit step function minus, and then 1 over omega n, and this is sine omega n t. Yeah. So okay. So notice there is some error actually. So if you factor it, it looks like a over s plus bs divided by s square plus omega n square. So we should have s here, yeah. So not 1, but we should have s, so that we have s square here, and like that one. So instead of omega n, we will have s here. So s here, so that no need of doing this one, and what we get here is simply s over s square plus omega n square is cos omega n. So we get here cos omega nt. Yeah. So like this. Okay. So given the solution now, xt equal to f naught over m omega n square ut minus cos omega nt. If we are writing for t greater than 0 only, yeah, so in that case we know that ut will be 1. So ut will be equal to 1 for t greater than 0, right? So we can write 1 basically. So we get xt is equal to f naught over m omega n square 1 minus cos omega nt. Now we can do further simplification. What we see is f naught over m omega n square. So we can also replace m omega n square with some value which will be more appropriate, and you can recognize it very readily. Yeah. So let's see what is the meaning of this one. Okay. So simplify further. Actually, what we meant is basically what we have is xt is equal to f naught over m omega n square. But m omega n square. So we can we write in the different form? So we know that is k over m equal to omega n square, right? So k is equal to m omega n square. So instead of m omega n square, we can also write it as xt is equal to f naught over k, and then we have 1 minus cos omega nt. Yeah. So then what is the meaning of that? What you see is basically the solution is xt equal to f naught over k minus 1 minus cos omega nt. We want to interpret the solution. So xt equal to f naught k 1 minus cos omega nt. So that means automatically it will satisfy if t equal to 0, you put this becomes 0. So how will it look like? So before the force is applied, this is t and x. So before the when the force is applied, x0 is 0. So this starts from here. Then what happens? Then as t increases, so from here you can also write in two form. One is basically the mean position. So you applied a force of a value f naught. So what it will do? It will change the mean position by f naught over k, right? So f equal to k times x. So mean position changes. So a spring mass is there, and we apply force to the mass. How much force? F naught, constant force. So for if you apply a force to a spring f naught, the displacement will be f naught divided by k. So this f naught divided by k is the displacement one spring will have you applied force f naught. So that really means this constant term here, that really means first of all, first effect is the mean position changes. Mean position was earlier here. After that, applying the load, so if the spring is like this one, or like this one, so what it does, if this is the earlier mean position, when you apply the load, first this mean position it will change, right? So this will be f naught over k, and about this point now sinusoidal displacement will start. Yeah, and about this point, so now at this point this is 0. Yeah, and now x dot x dot 0, if you put x dot 0, so x dot 0 is, x dot 0 should also be 0 because this is the initial condition we gave. Okay, so this will be something like, this will go like this. So on. Yeah. So that the velocity, the slope is 0, so velocity is 0. Yeah, and then x0 is also 0. So this will be the what the response looks like. This is the response with unit. Okay, or a step unit basically. So we are talking about a step in a step response to a step input. Means f equal to f naught ut. That's what we mean. Yeah? Means at t equal to 0, suddenly a force is a constant force is applied. So that's what it means, the step inputs. Suddenly at t equal to 0, you apply a load. Then the solution will look like sinusoidal only, but we have the cos, 1 minus cos omega in term. So that really means by applying the load, in sinusoidal load, what happened? When you apply harmonic load, then what happened? Mean position remains the same wherever the initial position was, like x equal to 0. If you apply the sinusoidal load, then the mean position remains the same. But when you apply the constant load, mean position will first change, and then about that sinusoidal load will start. Okay, so it's sinusoidal load only, but however, just because the initial conditions are given, hence it will start like this one. Since it starts like this one, this will be a cosine function in that case. Yeah, so that's what it